And we saw that Lie algebras made life a lot easier because we start working with linear vector spaces rather than some horrible non-linear thing. And so, and the key was that you get a group there is a nice relation between group elements and exponential of, so let us say that you have generators T A's and some parameters alpha A's. Did I use uppercase or upper index for T A last lecture? Then we do, let us stick to that. Okay. So, what this tells you by looking at it in this form, what you realize is that this is a group element. So, you can actually write the parameters in this form. And toward the end of last lecture, I told you that you could I asked you to consider something like this for SO3 or SU2, I guess SO3 is good enough, and T A B C you take it to be epsilon A B C with A B C everything running from 1, 2 and 3. Okay. So, for instance, so this would tell you that you could write a group element of SO3 in terms of something like this. So, for G of SO3. So, again like I pointed out, this is in some representation. So, this is a 3 by 3 matrix. So, this is in the 3 dimensional representation of SO3. And one more bit on notation, when you write the Lie algebras you use lowercase letters and uppercase for this. So, the group SO3 would be written this way and here I would mean the Lie algebra. Okay. Some books use some kind of different script, some other font, etc., but I think for writing at least you can uppercase for group and lowercase for the corresponding Lie algebra. Okay. This is standard notation, and so we are in a 3 dimensional representation. So, the group also, so if you through the exponential map, so I will just write the same thing alpha A T A. I am not putting an I out here, I am using the math convention just for now. So, this would give you G of alpha A, and if you just go ahead and rewrite alpha A as follows, I write this as some angle times n hat of A, where n hat of A is such that okay. So, then you can rewrite this. So, it is still 3 parameters because if I just wrote alpha A, it is alpha 1, alpha 2, alpha 3. So, all I am doing here is calling theta the magnitude of alpha A in some sense. If I define magnitude to be alpha 1 square plus alpha 2 square plus alpha 3 square, and then I just write this. Okay. So, now we know that this SO3 is just rotations in real space, and so this you can see now I have written it in a particular form. This so we know in 3 dimensions any rotation can be written as a rotation by some angle theta about some axis n A. Okay. So, now you can see that and I believe I have given this expression in one of the assignments. I asked you to work it out, I think so. If I have not, it does not matter, but so now this is what we would have called in our earlier notation, we would have called this R of n hat and theta. Okay. So, we see a nice connection between what we had seen in sort of in more elementary courses or even earlier in this course, and something much more starting out from a much more abstract setting. The advantage of the abstract setting is this kind of formula holds for Lie groups, for arbitrary Lie groups. Okay. So, for instance, if I take SU3, we know nothing about it at this point, we except for the fact that it is a Lie group, and it so what about SU3? So, first thing we can check is that the dimension will be 3 square n square minus 1. So, that will be 8. So, it is a set of n by, so the natural representation is you look at 3 by 3 Hermitian matrices that are traceless. That will be the Lie algebra, okay, similar to what was antisymmetric. So, the dimension will be 8 and you need to choose some bunch of 3 by 3 matrices, and so let us just call them instead of calling them TAs, I will just call lambda A. A runs from now 1 to 8, but there will be some I j index, I and j run from 1, 2, 3. So, these are some 3 by 3 matrices that satisfy this property, which will form a basis for this thing. So, so the statement would be, if you wanted to write an SU3 arbitrary SU3 element, just one second, I will not say, I should say skew Hermitian or anti Hermitian, because I am not putting an I, okay, or we leave it like this, and yeah, let me stick to the physics convention now. I put an I out here, okay. So, this is physics convention. Well, this is a maths way of writing it. Okay. So, you can see that sorry, not T A, lambda A. So, if lambda A is Hermitian, I times lambda A will be anti Hermitian in a trivial fashion. Okay. So, now you can see that so in your assignment you will see that I have given you a bunch of a particular representation of these 8 matrices. These are called the Galman matrices. Galman is a very important name in this in high energy physics. One of the reasons is that he actually brought about the idea of using groups to classify the particle zoo. Okay. So, what happened is that they used to find what are called resonances every day, and it looked like should we call them new particles, etc., because people did not know about quarks or anything. This was before the quark model, and so what he did was he realized that there is some underlying SU3 symmetry, and it goes by the name of, he coined something called the 8-fold way. This 8 I mean is related to this, and so that and he introduced this particular set of basis vectors or basis vectors for the Lie algebra SU3. Okay. But you do not need, I mean the point I am making out here is that we do not need to remember anything, you can just write out the group elements. But there is one tricky part in this whole business. If you are asked what is the values that what is the range of values alphas can take such that you get a single valued this thing. So, out here it is easy, I will tell you the answer, theta goes from 0 to 2 pi, it is identified. But if you go to SU3, it is not so easy. So, local properties you can capture, but if you want global properties, which means which tells you things like what are the ranges values these various alphas can take, then you will see that things are more involved. But at least notionally you can see that you are able to write out group elements which satisfy all the product rules which are required. Okay. So, now coming back to the original problem, we wanted to parameterize find a nice way to choose fluctuations when you have symmetry breaking. Okay. So, let us assume, so let us return to symmetry breaking. And let us say that H is some strict subgroup of G, and let us assume so G, as usual, G is the symmetry of the thing and H is some subgroup which is preserved by the classical vacuum, and we will assume, so this is the symmetry of the theory and this is the unbroken part. Further, let us assume, for simplicity we will assume both are Lie groups. Okay. And now one more point here is the fact that H sits inside is a subgroup of G sort of tells you that the Lie algebra of H will also be a subalgebra of Lie subalgebra of G. What is the statement? What you will say, so when we looked at, when you said subgroup, if you take two elements H1 and H2 which are in H, you take their product, the group composition, it will stay within H. So that guarantees, so that via the exponential thing you will see that the Lie bracket or the commutator of the Lie algebra elements should stay. So it is just the closure part you have to check, but the closure at the Lie algebra level is done by taking the Lie bracket or the commutator of the Lie algebra elements, and while in a group you is just a composition law. So in other words, what you will so let's first go ahead and write, let's say that let's use little g. Okay. So we will write something like this: H is a sub algebra of G. So this I am replacing this statement by the Lie algebra. So now we can go ahead and let us say that we choose T, let me choose capital A, okay, and let us say that A runs over some things, it runs over dimensions of G, and let us say that this has a bunch of generators. So this is a basis for this thing. Similarly, I can have another T, let me use a little a index, and A will run over dimension of the Lie algebra H, okay. Because it is a strict subgroup, obviously this dimension will be less than this, and we can be clever enough, because this sits inside this, we can always adjust it such that the first H elements of this, okay. So we can also write A, I can break up the indices or the generators A and A dot, where A runs over 1 to dim H. So that is the set of generators which are in H, and A dot are the set of generators which are not in H. So they belong in some sense, morally speaking, to the coset, the directions along the coset, okay. So elements in H, rather group elements. So now we can see the very easy things, lot of simple things can be done. We can write a group element, so an element like this, e power okay, let me put the I, stick to the physics notation, alpha a T a. What would be this group element? Where would it belong to? It will be in H, okay. And suppose we wanted elements in G mod H, what about elements okay. This is what we wanted to isolate, right, we wanted to get the flat directions, etc. Okay, that is what we wanted. Yeah, okay. So H is a symmetry of this thing, and so we just want to write out. So you can see that a natural choice will be to write an element of this form, okay. So this is the index generators of the Lie algebra, not in H, okay. So you can see, morally speaking, so how do you understand this? The most general group element would be something like this, but now I can write I want to get the coset, but I can keep acting on it either from the right or left, does not matter which way, I can keep acting on it, and you can see that I can always adjust it such that this term goes away, okay. So this is a representative, okay, of, or equally well I could have written the most general group element, I could write it out in some form like this, nothing wrong with writing it even this form. Okay. So now you can see that the Goldstone modes came from exactly these guys. Okay. So if you want, so what you would do is you would write out these elements explicitly outside. So if you have some vector v, so this is some vector in whatever representation it is, it's acting on this thing. So what I would write is the fluctuations I will write as v plus eta, okay, where eta would be like the analog of the radial directions times e power I alpha a dot t dot, and eta, the number of eta fluctuations will be the whatever is the appropriate things, but this you can pull out explicitly, and you can see all the non-linearity etc. that you need is taken care of. So this is what one means by choosing a clever parameterization. Okay, and that's why the Lie algebraic structure is very useful in even just writing something like this. Okay, and then because you have chosen things properly, everything will work out. Okay, so so we'll get back to where we will see more general symmetry breakings etc. and in this course, and during that time you will see me explicitly work out examples of this. Okay, but you could for instance ask what happens if if I have 3 scalars in SO3. So so exercise for you, choose G to be SO3, 3-dimensional representation, the normal vector thing, and H to be SO2. So this is nothing but choosing one vector, so that so this would be the rotations, and so you write out, you can, I think it should be by now very easy for you to write out something and just work out, verify Goldstone's theorem for this example. For an example, you can construct a Lagrangian which has this invariance. So you so and the scalar fields will be some phi. Choose a suitable potential. You can even choose my favorite 5/4 potential if you wish, which has that invariance. Okay, so this is a good fun exercise, and I am sure we will look at this example. Okay. Yes.
So it will be the A indices, not the A dot indices. What should I do?
Have I mixed it up? Yeah.
A dot are there in the solution. A is what is broken.
We rotate by the unbroken.
Then the
We rotate the solution by the unbroken.
No, I think it's correct, because you just look at it, right? If I put A out here, it's a symmetry of this thing. So trivially, so if I have something, just forget everything. There is a statement that it's a symmetry. So you write the most general group element action on V and you see what you get, but the V goes off. Okay, I think I am correct here. Okay, so before moving ahead to more general things, I would like to take a step back, and like I said in my summary of what we have done so far, we are moving on to understanding vector fields, and so I would like to complete the discussion of looking at the symmetries of just the electromagnetism and getting the various currents etc. This is something you have done in your assignment, but I would like to go over the solution to that, and so that is what I will do in the next half hour or so. And since you people have worked through quite a bit of the details, I will just go over points which I want to emphasize etc. Okay, so the Lagrangian is very simple. Okay, just to add some structure to the, so this what would be the Lagrangian density for pure electromagnetism or U1, but I have also added a mass term. If you add such a term, this Lagrangian goes back to Proca, so it is called the Proca Lagrangian. As I mentioned, just as a quantum field theory, this thing is sick. Okay, without it's like, I mean, this breaks gauge it's not invariant under local transformations because of this particular term. There is a potential for the gauge field. So you know that this is bad, but from a viewpoint of just taking a classical Lagrangian, getting it working out what the the currents are, etc., under various symmetries, this is a perfectly good thing to start with. And also you can go ahead at the end of the day. There is one part where when you set m equal to 0, something nice happens, and that means something. So, okay. So what are the symmetries? So the first symmetry, of course, is translations in space and time, and okay, I will use epsilon because I will use a for the arbitrary parameter. So epsilon is some constant parameter in this thing. And so this is one symmetry. The other symmetry which we will look at is x prime mu. Let us just write it this way. Okay, so we always work to first order in these parameters. So epsilon and lambda are supposed to be first order parameters, and so for here there might be no higher order terms, but in this case there will be more terms. And we also saw that this lambda mu nu was, if you lower the index, you get lambda mu nu, it is antisymmetric. We have already seen this. Okay, so and the last symmetry occurs only when m is equal to 0, and that comes from and that is just the usual gauge symmetry, which is, I think I use alpha or something, but it does not matter. Okay, so this is local gauge symmetry. Okay. So the first point here is to work out what the equations of motion are, but I do not think I will work it out. It is rather simple, but yeah. So what I will do first is to work out the the current for translations. So we need the master formula, which we had worked out several lectures ago. Okay. So the only change I did in the master formula is said that we have done it for scalar fields phi a, but it does not make any difference. I replace phi a by a nu. I mean, it is the same thing. Nu, think of nu as an index like a. So the same formula goes through. There is nothing deep in this whole thing, whole business. And delta bar was the function change in the functional form. Okay. And yeah, so one more thing we need to know how the gauge field transforms, but I prefer to think of it in more general settings, like in general theory of relativity, but it holds even these two are also examples of coordinate transformations. So they are, so I will write something more general than okay. So all you have to do here, if you want to work out what it is under translations, is to look at dx prime by dx this thing dx nu, and what do we get? We get delta out here. So for translations, we see that a mu . but for Lorenz transformations, okay. So, okay, you may think I have from here it is easy to get dx prime by dx nu, but for small thing you can just invert it and just get put a minus sign and you will be fine. So, since I want to write it in this form, what I will get is a prime mu of x prime will be equal to okay. So, now you can see that the first time we are actually seeing something more than normal. So, this looks like exactly like you had for a scalar field, but out here the fact that this index transforms under Lorenz transformations shows up here. So, what is it we need to do? Really the only things we need to work out are and to write out what this A will be, what is delta bar and these things. So, I just do these two things, and so first thing to work out is what is A mu. A mu is nothing but epsilon mu out here, and out here A mu okay. So, this is, by the way, is this, was that my notation? I mean, am I okay, or is there a sign issue? I am okay, right? Well, if there is a sign issue, I will fix it later, but right now it is not so. I mean, it is important, but I do not think the world is going to. So, let us first do this part. Now, this is something lots of students have trouble with, what do I do with this? The first thing is, so I have to go ahead and do the variations in here, and this has d nu, a mu, etc. You have dummy indices, all these things. So, first thing you should, if you are totally confused, is to not do what I have. Okay, here I am interested in d mu, a nu, and these are all dummy indices. So, first thing to do is to write this as rho n sigma, something else. Okay, then you expand this. Each of this is 2 terms, you get 4 terms, okay, and each one of them will give a contribution, and they will all add up, and it will eat up this 4, and that is about it. Okay, so, you will end up getting minus okay. So, you need to fix, you have to look only at one of the terms. The minus comes from here, this minus, okay. Sorry, f mu nu, thank you. Sorry, yeah. I was intent on getting the sign correct, I wrote something wrong. Okay. So, but the thing is, I never like to explain in more detail how this 4 goes away, because everybody has their own way of doing combinatorics. I know that I cannot follow someone else's combinatorics. What I do is to do my own and then check. Okay. So, but this is something which you should do once in your life, actually expand it out in gory detail, write out every one of the 4 terms, write the delta functions, everything, and see that it works, and then after some time you, I mean, you can just do it visually. Okay, but the first time around it is not something where this step to this step, I mean, it is okay to spend 5 to 10 minutes. Okay, it is not, do not feel ashamed that oh, it took me so long. Okay, but after a while it will be like 10 seconds. So, this is one bit. The next part is to work out delta bar of a mu, and that is defined to be so it is a function, change in the functional form. Okay, this is the definition. So, for translations, it is similar to what we got for a scalar field. I will just jump some steps and do it from memory. It was minus a mu d mu, Okay, so it was, so delta bar of A mu was minus A. So now there is a free index mu, so I should use some other index. So let me call it d nu. Okay, it's a little bit more involved for Lorenz transformations. So for Lorenz transformations, so we have to make so one term. So let us first forget. So there will be one term which will look exactly like this, which I will write out, and A nu is just epsilon. So we go back to the constant parameter, and delta bar A mu will have one piece which would be minus A mu. So that is minus A nu lambda nu rho x rho times d nu A mu. So I have just written A mu d nu d nu rho, but A nu is this. Okay, but I get one more piece which comes from this. Okay, we are ignoring all order lambda square pieces. Okay, so this is the biggest change that happens, because you have this has an index which transforms. So until this point everything went like it went for a scalar field. Okay. So first step is to get the stress tensor for this. That's just the conserved current for under translation. So let us get the stress tensor. Okay. So now I will not I mean putting all these things into this thing, and there is only one. So there is this parameter epsilon which is a constant. Okay. Remember a mu in general is not a constant, because here is an example where a mu depends on x. So you cannot pull out a mu outside the derivative. You can pull out only constant factors like lambdas. Okay. So what you get is T rho mu equal to okay. So this is what you get, and the conserved current here is d rho. So the rest of this talk lecture, rho will be the conserved current, this thing. Okay. So this is the point. So we can look at this and we can just write out, we get minus f rho sigma d mu a sigma minus eta rho mu L. Okay. So first thing you observe is that it is not symmetric anymore. Okay. That is one issue. So okay, which was true for the scalar fields. So here is one concrete example, but there is one more issue, especially we know that this is a toy model. The model we are really interested in is when m is 0. When m is 0, you look at the energy momentum tensor out here. This is not gauge invariant. This is f, which is invariant, but this is not invariant. It is also not gauge invariant. Okay, so set when m equal to 0. Which is not a very nice thing. I mean, so the question is there some way we can actually make that f, okay, and along the way also make it symmetric. Okay, and so the answer is actually more or less staring you in your face. You can actually figure out these things, but there is some logic which goes behind what you can add. Okay, but at the end of the day, this is the conserved current which was given to you by the Noether prescription, I mean the formula. So now the question is, can we do something to it such that the charges are not affected? The charges should not be affected, but some nice properties are recovered, such as we recover symmetry and may even gauge invariance. In this case you will find both of them come in one fell swoop. Okay. And we can go ahead and also work out what the Noether current for currents for Lorenz transformations. Okay, call them this thing. So again, rho is the, so this is such that d rho m tilde rho mu nu is 0, and this is antisymmetric in mu n rho nu, because the lambda is, so the parameters which come with this. So this turns out to be what am I writing? X mu t rho nu minus x nu t rho nu. Okay. So again, when you do this, this term comes from exactly this term, it is similar to the other guy, but this piece will give you an extra term, and it is better to write that out. Okay. So the thing is, you do get something, but the point here is it actually consists of two parts. Okay. This piece looks pretty much like r cross p in physical space, this thing. So this has, morally speaking, the role of orbital angular momentum, okay, while this guy, so whenever I say angular momentum, I mean a generalization. My angular momenta has 6 components, because we are in 3+1 dimensions. It's not, so rotations are examples of them. Rotations only have 3 parameters. So the usual angular momenta which we discuss have only 3 components, okay, corresponding to rotations, but we have also 3 more currents which come due to boosts, right. So there are 6 of them, and so what one does is to use in relativistic field theories, whenever we use the word angular momentum, we mean a generalized angular momentum. In fact, this is the angular momentum, okay, in that setting. Okay. Yeah, and so now this has to do, so this is what we will call, but you can see orbital angular momentum is not conserved, and this came because this object has this extra transformation. Where does this come from? This comes from the fact that this has it transforms under Lorenz transformation. It is an index which transforms. When we go to fermions, fermions carry spinor indices which again transform exactly like this. I mean, when I say exactly like this, it is not a vector index, it has a similar property. You expand it, you will get lambda, and except here these indices would be spinor indices as opposed to vector indices, okay, but the structure will be similar. So for fermions also you get the same story, you get one more piece for the same reason, okay, and so this is what we should call the spin angular momentum. Okay. So now what we will do is to recover symmetry of the stress tensor or the energy momentum tensor. We will modify it to get something. So we will construct something which we will call theta mu nu, which has the following properties. First thing is it is symmetric and it is conserved. I should say rho mu. the 4 charges, the charges, so the charges associated with the theta 0 mu integrate or whatever agree with T 0. Okay. And some more properties we will put in m mu nu, m rho mu nu So, this other term is just anti-symmetrizing with mu nu, I mean there is nothing to remember. Okay. So, this m is not quite m tilde, that is why there is a tilde, but the key point is that the charges again and the charges of m agree with those of m tilde. Okay. So, the property 2 actually is most gives you a hint as to what you have to do. You want the charges to be conserved. So, what you do is you suppose we did this, suppose we look for something like this theta mu nu. Actually, there is a fourth one which I could add, which says that it should become gauge invariant. Okay. In fact, it is a bit of a cheat in the assignment, I did not write that, and okay. So, theta mu nu plus T mu nu and H rho nu is totally antisymmetric. So, if you have this is like a total derivative. So, if you add things to it and you do an integration, you will find that the charges this gives surface terms, and if your fields drop off, which is what you assume at infinity, then there is no contribution coming from those. Okay. And so, we need to figure out an H rho of nu. But actually it is very easy to ask what that would be, because you use my trick, which is to say let us look for the gauge invariant guy, and up to some sign you will see that H if you plug this in, if you plug what is it this value of H into this, you get this theta. Okay. And theta is really, if my memory is right, theta what did I erase? I forgot. Okay, f mu sigma, that is what it is. Okay. And you can also, so then it is kind of nice, you get something which is gauge invariant, and you have this thing, and you can actually go back and look at what you get for theta 0 0. Okay. And think of it in terms of electric and magnetic field. So, I am right, I will be in your assignment, I am sure you put m not equal to 0, but for my class I will, for this lecture I will just set m equal to 0, because I can write the answers, otherwise I have to look up some notes or something, I do not remember the answers, but this is like half okay. And what was so again this tilde here implies I do not know the factor, it is probably half, was it half? Okay. But the key point here is that you end up getting something which is positive definite. Okay. What about theta 0 I? It is a pointing vector. Okay. And another thing which is very interesting is that theta I 0 is equal to this, but it has a different meaning, you see, in some sense it also is the energy flux. So, it has a dual role, it is a conserved charge. So, you can think of this as momentum carried by the electromagnetic wave. You could also think of it as the energy flux when you think of it as a low this thing. theta ij is something which you should write out in terms of electric and magnetic fields and see for yourself. It is a little bit of a mess, but it is okay. I mean, so it is a momentum flux. So it has two directions, one for the momentum and one for the physical directions of the plane. And yeah, so this is actually important. This tells you that the field carries some energy and also can carry some momentum. In fact, you can come up with examples if you look at books like maybe Jackson electrodynamics. I am sure it, or even Landau and Lifshitz, I am sure they discuss examples where you actually, if you just looked at particles, charged particles moving, you will think that energy is not conserved or momentum is not conserved. Okay, but if you actually go ahead and look at the combined combination of the energy of the particles plus the field energy and the field momenta, you will find that energy and momentum are conserved. There is a problem with saying what is the field due to the what is the, suppose you have a point charge, there is an electromagnetic field all over. If you try to ask what is its the total energy, it could be infinite. So you need to regulate a bit. So one way to regulate it, put it in a big box, and the box is big enough that size should not matter, and that is not relevant for your this thing. And so you can actually come across situations where this the total energy which is conserved is the energy of the particles in this thing. So at a fundamental level, you can see that this is proof, if you wish, to say that this is the object you should call energy density, of course here, and this is the momentum density. So there are actually in classical electrodynamics enough examples of this kind. Okay. And the last bit of thing which is actually also, yeah, before I forget, there is actually a completely different definition of the energy momentum tensor. And so the thing is that in last lecture we discussed how local internal symmetries, if you make them local, okay, what will happen. But there was nothing to say that you cannot make translations or local, okay, but that will naturally take you in some sense will take you to the realm of general coordinate transformations. So that is the correct thing. So in some sense general coordinate transformations subsume both translations and Lorenz, there are special cases of that. So you will ask how things transform under general coordinate transformations, and then if you want to make things so there will be analog, you have to introduce a field, the corresponding field that will turn out to be something called the metric. Okay, so you replace, so the dynamical field will be eta mu nu replaced by something called g mu nu. Okay, it is a little bit confusing, it is not a vector field, it is a spin 2 guy, it is symmetric, etc. Okay, but even if you went, this is sort of a particle physics way, anti geometric in some ways. What we are doing is to just say that what will happen if you convert something symmetry to a global symmetry. That is not the way Einstein thought about the general theory of relativity, but even this sort of approach leads you to a similar thing. And so what you do is now you can ask give me some Lagrangian, can I make it locally invariant under these things, and you couple it to a metric, and so you can write something in again in a minimal fashion. So you define T mu nu as follows. I think there is some square root of minus g factor, g is determinant of this thing, and okay, upper lower bad form on my part, but this by definition is symmetric. Okay, now it is a big deal to show okay, why is this equal to that. Okay, that is a different thing, but so there is a straight ahead way of getting a symmetric stress tensor by thinking of it as the current which couples to gravity, just as we got the current which couples to, I mean, so in that sense it is similar. So so the coupling, another way of saying it is that the you take g mu nu to be eta mu nu plus some small parameter h mu nu, and you want the linear coupling such that it is invariant under general coordinate transformations to first order, and there is a minimal way of doing it. Okay, and so what you will find is you will get S will be S naught plus rather L, where L naught is where you use eta mu nu whatever you wrote, plus up to factors T mu nu H mu nu. Similarly, as compare with for gauge symmetry, again it would be similar. There are infinite order terms, but only the linear pieces again gave you J mu A mu. Okay. So, this will naturally give you something symmetric. Okay. So, the last bit was you are asked to find the trace of this theta mu nu, okay, and you should remember to trace with eta, not with so trace of theta mu nu is not the sum of the diagonal terms or whatever. We have discussed this before. It turns out that this is equal to 0 when m square is 0. Does anybody know why? Okay, I will give you the answer. There is a new there is an extra symmetry, at least at a classical level, which is scaling. Exercise, show that the conserved current due to this symmetry, scaling symmetry, is actually the trace of this conserved current or charge or whatever. So, you will see that is traceless. You can prove that. Okay. So, this is actually indicates that you have this thing. So, you will find that we will see more general things when you take the non-abelian gauge theories. That means, you have a non-abelian group, Lie group, which you gauge, you make symmetry local. You will find even in such cases classically. So, if you take SU3 for instance, you will find that classically the trace is 0, but quantum mechanically that need not be 0. So, a classic example of that is QCD, where the group is SU3, and it is known that there is a natural scale. So, one more way of understanding is when m square is 0 is there is no length scale in the problem. Okay. This is true only in 3+1 dimensions, but if you go to other dimensions that is not true. So, this is actually dimension true only in all other dimensions. Gauge couplings are dimension full. We will do some analysis at some later stage. Okay. So, I will stop here.